Let's see. Okay, let's say that I were to tell you that that we surveyed people that worked in the nickel processing industry, maybe plating, nickel plating, right? That might be a conceivable place that some of them might be working. They might work with a lot of nickel salts that they dissolve into, put in solution. They drop things into them to plate them and so on and so forth. They do electrical plating with them and so on. But workers there have an exposure, a respiratory exposure to dust that contains nickel. Nickel is associated with nasal and pharyngeal cancers. I'm going to spell that. I'll come as close as I can. Cancers. So let's say that there's so many people that work in that plant, work in that facility. They're office workers, they're accountants, they're so on and so forth, they're business managers, and they don't have any exposure to nickel. On the other hand, you have workers that work in the plant floor that do have a significant exposure to nickel, right? So we can have people that, for instance, are exposed to nickel and developed, nasal pharyngeal cancer. We can have people that were not exposed that maybe just by chance for some other reason randomly developed nasal pharyngeal cancer. And we may have the opposite. In other words, people that weren't exposed that had the same kind of situation. So we have 4 different outcomes, similar to what we were looking at with our diagnostic tests: true, false, true, negative, false positive, false negative, so on and so forth. Okay, so let's say that I have 100 workers altogether. And out of those 100 workers, I find that 20 of them developed nasal pharyngeal cancers or precursors. Maybe I'll make it a little bit more realistic that you wouldn't expect like to get 20% of the workers winding up with nasal pharyngeal cancers, but maybe like you could observe precursors, changes in cell structure and so on and so forth. So 20 of them developed it, 80 of them didn't develop it. So 20% developed it. Okay, so now the thing there is that now what if I told you that out of those 100 people that we were looking at, that 40 of them were exposed and 60 of them were not exposed, right? So I'm going to draw a line through here in the middle, right? These are the people that were exposed to nickel, exposed to nickel, or not exposed. And I'm going to draw a line down from here. And out of those 40 people, I'm going to say to myself, how many would I expect to develop these signs of precursors for this cancer? All right, I'm going to say cancer plus, cancer minus for precursor, right? How many of them would I expect to develop these precursors out of 40 people if there was no association? Nickel really didn't have anything to do with it. It was some other exposure that was causing the disease, right? So so let's think about this. What is the prevalence in this population of nasal pharyngeal cancer? It's 20%, right? Exactly, 20 over 100 or 20%. Okay, so you guys are with me online, right? Just if you can just type in there, give me some encouragement. It'll help me out so I know that things are happening there. Okay, so 20%. So out of the 40 people, as you said, you would expect 8 people to develop nasal pharyngeal cancer, and out of those 40 people, you would expect 32 to not develop it. Now, out of 6, what about the people that are not exposed? Well, it's not nickel that's causing the issue. If there's no association between nickel and that form of cancer, I would expect 20% of them to develop it as well, the same percentage as the people who are exposed to nickel. Okay, and that would be 48. So if I add this all together, it should add up to 20 and 80 for a total of 100 people. Kind of looks like our diagnostic test a little bit, right? Okay, so now that's very interesting. This is our expected outcome. Or I'll put it another way, I'll phrase it another way, our expected values. Okay, so now let's see what really happened. Now I'm going to take a look at the diagnostic test for these 100 people. And as it turns out, the real situation is See, we had 40 people that were exposed and not exposed, and cancer and no cancer. Okay, cancer plus, okay, and 60. Okay, let's say it turned out that 12 people out of 40, that would leave, out of the 40 people that were exposed, that would leave 28 people. And let's see, 60 people, 60 people, so if 12 people were exposed, there are 20 altogether developed the condition. That would mean that there would have to be 8 people in this group that actually, it doesn't, I don't even have to come up with that. It's 40, all I need is to go across. So I'm going to say out of 60, I'm going to say, no, I want it to add up the same way. The actual observed values were, let's see, 8. And here would have to be, this is going to be 20, this is going to be 80. So this would be 52. Okay, so we got 100 people again. So instead of seeing 8 out of 40, we see 12 out of 40 in the exposed group instead of seeing 12 out of 60, which means that both groups had the disease at the same prevalence rate. Instead, we find, in fact, in reality, our observed values. I think my pen is starting to get a little weird here. Values. I'll try going straight up and down. Our observed values showed this distribution to be like this. So how can I describe what's going on here? What's the comparative rate of cancer in the exposed group versus the unexposed group? Well, one way that I can do it is to describe the risk for people that were exposed versus the risk for people that were not exposed. So let's see, what's the risk for people who were exposed? The risk for people who were exposed is 12 out of 40, right? Which is equal to, let's see, what is that going to be? That's going to be 24 plus 6 is going to be 30%, I think. Am I right? A little bit more? Hang on, I'll use my calculator. I'm a little jangled still from trying to drive through that mess outside. So let me go ahead and use my calculator. Right, 12, 80, 24 plus 26. I think well, I'm not being very successful with this. There we go. Oops, I lost it. Where'd it go? You can see, I can't see it. Oh, you know what it is? It's behind my control panel. That, on my screen, I have a control panel, so I can see the chat box and stuff like that. So it's back there. So 12 divided by 40 equals 30%. I was right the first time. Okay, so the risk for people who are exposed is 30%. What's the risk for people who are not exposed? Well, for them, it's 8 out of 60 people develop that condition. So 8 divided by 60, 13%. Check it. 60. Good. Okay, 13.333. Okay, so I'll call it 13%, just since you got the answer quickly. So that's 13%. So the risk if you're exposed is 30%. The risk if you're not exposed is 13%. Okay, well, it's very convenient. It looks here like that exposure puts you at a greater risk for developing this cancer. Now the problem is that if we really sampled 100 people at random, we might get, it would be unusual at best for us to get exactly the same percentages, same percentages of people getting the disease just by doing a sample like this of 100 people, even if there was no association between nickel and this kind of cancer. In other words, we'd have to be awfully lucky to get exactly this outcome when we sampled 100 people, even if there was no association, right? So is this difference here big enough for us to say that there is an association between nickel and cancer, right? Is that big enough association? Well, one of the things we can do here is we can take these two risks, right? The risk if you're exposed over the risk that you're not exposed, and that's going to be equal to 0.30 over 0.13. 0.13, I'll even add a couple of threes there since that's what it looked like. And let's see what's it going to come out to be. So it's going to be 0.30, 0.3 divided by 0.133 is equal to about 2.26, right? 2.26. So the risk of you developing this form of cancer, if you're exposed to nickel, is 2.26 times as great as if you were not exposed. That it has a special term. That's called either the risk ratio or the relative risk. Okay? Risk ratio, right? Means just you're dividing one thing by another. So that's a convenient way to describe something, right? I mean, here we had these kind of numbers, 30%, 13%, but now you're able to quantify the risk. That's nice. We do that all the time. You know, smoking increases your risk of getting lung cancer, I think 7 times versus someone who's not a smoker, and asbestos 5 times. And if you smoke and you're exposed to asbestos, then it's 35 times the risk of not people who had neither exposure, and so on and so forth. It helps us understand the risk a little bit better, right?
Always the expected value, the relative risk is 1.
That's a good point. That's exactly what we're going to look at now. What if there were no association between nickel and this form of cancer? What would we expect the relative risk to be if there's no association? If there's no association, you expect to say, get them the same percentage of people get cancer that are exposed as don't get exposed. So we would expect the relative risk to be equal to 1. Okay. Exactly. Well, here's the point. We want to quantify how likely it is that we're going to be wrong if we accuse the nickel industry of causing cancer, right? So, just like our hypothesis test when we were working with numerical variables, a mean, we want to be 95% certain that there is a risk, that it does increase the risk before we reject our null hypothesis. What's our null hypothesis here? Our null hypothesis is that there's no association between nickel and cancer. Another way of saying our null hypothesis is that the relative risk is equal to 1. So our alternative hypothesis is the relative risk is not equal to 1.
So expected value is null hypothesis. An alternative is observed value.
Right, exactly. Okay, so now, yeah, but now I have to quantify this. Well, the problem here is that these are proportions, right? We need to find the probability that we would get with this sample size proportions that are different. We did do some work with proportions before. We could find a confidence interval, right? And in fact, when we calculate relative risk, we also calculate a confidence interval for the relative risk. So let's say in this case that the 95% confidence interval for the relative risk turned out to be 1.5 to 3.2. Well, what would that tell us? That would tell us, since 1 is not within our confidence interval for 95% certainty for the real risk ratio, that we can reject the null hypothesis. Now, if our confidence interval were 0.8 to 2.4, well, if 1 is within that confidence interval, so we can't reject, we can't be 95% sure that we would be correct in rejecting the null hypothesis. In other words, we don't have enough of an extreme difference for us to have less than a 5% chance of getting that when there is no association with between these two things, right? We need to get that alpha below 5%. In other words, have our relative risk outside of the confidence interval. In statistics, very frequently, rather than use something called risk, many studies use something called odds. And odds are calculated a little bit differently. So, for instance, if I told you we went to Aqueduct and that Trotters at Aqueduct, right? No, that's Yonkers at Trotters, right? That's regular horses, regular horse. So we're going to bet it. We're going to go to Aqueduct when we get bet on a horse, right? On the tote board, you will see the odds for that horse, and if it says 8-1 or 1-8, right? With I forget which direction it goes. It says 8-1. That means that if the race were run 9 times, the horse would win once and lose 8 times, right? 8-1 doesn't mean it's 8-1. It's not a relative risk. It's an odds ratio, right? So that's the way you interpret an odds ratio. Why do they do it that way? Because then it's easy calculation. If you bet $1, you win 8. Bet $2, you win 16, and so on and so forth. So it's an easy calculation to be made. So how do we do that here? Well, the odds ratio is similar to the risk. We go to our observed values, and we look at our observed values, and we say, well, geez, we have 12 people who got cancer among the exposed, and 28 who didn't. So that would be our odds ratio. Our odds for people who were exposed is 12 over 28. And our odds for people not exposed is 8 over 52. Right? See what I did there? 8 over 52, 12 over 28, instead of 12 over 40 and 8 over 60. Okay, so let's calculate those. Okay, let's see if I can't get my calculator back. It's back under my, yeah. There. Okay, 12 over, whoops, 28 equals 0.4285. I call it 0.43. Put in the memory too. 0.42. I'll just call it 0.42, close enough. And this one was 8 over 52. Now, you should not round off like that. Do what I say, don't do what I do, right? I'm just doing this, I'm trying to get you this quickly, but I'm hoping you'll take it to a couple extra decimal places so you'll get a more accurate answer. 0.15. Now, my odds ratio is 0.42 over 0.15. 0.42 divided by 0.15, and that's equal to 2.8. So it came in the same direction. It's similar to my odds ratio, but it's not exactly the same. So this is my odds ratio, but both of them tell you the same story. They tell you you're at a higher risk if you're exposed to asbestos. If you're exposed to nickel of developing nasopharyngeal cancer, right? So the odds are 2.8. Similarly, the odds ratio, a null hypothesis for the odds ratio is equal to 1. And our alternative is the odds ratio is not equal to 1. And what would we do? Again, we'd calculate a confidence interval, and if it came out to be 1.2 to 4.7, we know we could reject the null hypothesis because we're outside of that range. Kind of a single sample test for proportions. What's that? There you go. Good. Right. So odds ratio. You'll see odds ratio. Personally, I think relative risk is much more intuitive than odds ratio is. In other words, it's easier for people to understand relative risk. 2.26 times is likely, as opposed to odds, which are a little bit harder to wrap your head around, right? Because it's like, the number of people who got the disease versus the number of people who didn't get the disease is the odds, right? So it's a little bit harder to interpret. Okay, so that's the way we might do that. Now, that's not the only way we can interpret these crosstabs as well. There's another statistic that we can use that's called chi-square. So I'm gonna get a new blank piece of paper here. Okay, let's see if it opens it up. I have to do it. Oops. I think I lost the other one, eh? Yeah, I did lose the other one. Okay, I got a new piece of paper here, and I'm gonna try and remember but I got. So let's say we started off with our observed values. We did a study and we surveyed people we did a retrospective survey and we studied people that were worked in this plant, and these are the exposed, and these are exposure negative, and this is cancer plus, cancer negative, and I said 40 and 60, the 100 people involved, and this was 8 and 52, and this was 12 and 28. It's a miracle I actually remember it. Okay, let's say that's all we know right now, because if we actually were doing this study, that would be all we would know, really. So before I start, I would say, what's my null hypothesis and what's my alternative hypothesis? Okay, and now we're going to use this new statistic called chi-square. Chi is kind of a big X, chi-square, capital Chi X. Well, null hypothesis is that there is no association between nickel and nasopharyngeal cancer. And the alternative hypothesis is there is an association, right? Just like everything else, we start with the equality and we try and reject that hypothesis so we can prove the inequality or come as close as we can to proving it anyway. So if I only know this, what were these called again? Were these my observed or my expected values? These are the observed values, exactly. What are my expected values? Well, before I started with it, because to illustrate this, I wanted to show you what the difference might be between the two of them and why what our null hypothesis really is. This time, I need to calculate what my expected values are because I don't know them ahead of time. I did the study. I didn't know how many people I'd get that had precursors for this cancer. How many didn't? I didn't know that this was going to be 20 and this was going to be 80 when I started. I didn't know that for sure that 40 would be exposed 8 because I just collected I set up my null hypothesis. I did my survey and collected my data, and this is what I wound up with. In order to figure out how far we are from where we would expect to be if there was no association, we would have to build another table called our expected values. Okay, so let's build a table with our expected values. So we know that we had 40 people that were not exposed, that were exposed. We had 60 people who were exposed, and we had a total of 20 people who had this precursor to this cancer, and we had 80 people who did not, right? So the idea here is that here's our observed values. What did we expect if there's no association? If the whole null hypothesis were true, how could I fill this table out? Well, remember what we said about the prevalence? The prevalence was 20%, right? So we could say, well, gee, 40 people were exposed. Out of 40 people, I would expect 8 people to wind up with this cancer. And that means I would have 32 that didn't. Out of 60 people, 20%, I expect 12 out of 60 or 48 to develop it in this group, which had more people in it as it happens. In other words, we would expect the exposed people to develop cancer at the same rate that the unexposed people did, right? So I have 2 boxes here now. What I would have expected if there's no association, what I would have expected if there is an association. So now let me think about this. I don't really expect that these numbers are going to be exactly the same. Again, if this is what I would have expected, well, just by chance, I might have gotten 9 and 13 and 33 and 49 or 10 and so on and so forth. Just because this is the prevalence doesn't mean I'll get exactly what the population is like when I take a sample, right? So there's a certain amount of chance in here. But you can say to yourself, the further away that these numbers are from my expected values, the less likely that difference is due to chance. In other words, if we had gotten 30 out of 40 people in the expected group and only 1 in the exposed group and only 1 in the unexposed group, gee, that seems like pretty strong evidence when I expected this group, this kind of layout here. So the further away each box is from the corresponding box in the observed and expected values, the more likely that it's because that there's an association between an exposure and the disease, right? So, in other words, it's more likely that the null hypothesis is not true and I can reject it, right? So, how am I going to take advantage of that? The way I'm going to take advantage of that, I'm going to go into each one of these boxes. I'm going to call it chi-square. Call this thing chi-square, and I'm going to say that chi-square is going to be equal to the difference for each one of these. And the difference, let's take a look at the difference here. 12 minus 8 is 4. 8 minus 12 is minus 4. 28 minus 32 is plus 4. 52 minus 42 is minus 4, right? Or the other way around, right? What happens when you add them all together? They cancel out, right? So you can't do that. So you have to square them. So we're going to take our observed values minus our expected values. I'm going to square them for each one of these boxes. I'm running out of space there, so I'm going to put it down here, square and plus. I'm going to add all these differences up. Well, if I square it, it's going to make the overall numbers bigger, right? So my chi-square is going to be a big number because I'm taking 4, making it 16, and adding them all together. I'm going to take each one of these and divide by my expected values for that box to bring it back into the range, the magnitude of the values I'm working with. So what would this first one be? It'd be observed. Observed minus expected is 4. 16 divided by the expected. In other words, 16 over 8. Okay, we okay with that? Okay, plus, what's the next one? I'm going to go to this box. It's going to be observed 28 minus 32 is 4. Squared is 16. Minus 4 squared is plus 16 divided by 32. That's 16 over 32. Plus, the next box here, 12, 8 minus 12 is minus 4. Squared is 16 over 12. Again, 16 over 12, the expected value. Plus, 52 minus 48 is 4. Squared is 16, 16 over 48. And now we're going to add all of those together, right? So this is 2, this is 2, this is 1/2, this is 1 point, what is it, 1.3? Okay, plus this is 1/4. No, 16, 32, 28, it's 1/3. Yes, 0.33. Okay, this is 0.23. Okay, so if I add all these together, it's going to be 2, 3, 3.67, 3.67 plus 0.5 is going to be 4. I got that right? 4.17. Yeah, look right, 4.17. My chi-square is equal to 4.17. Right now, in order to say whether I can reject the null hypothesis or not, I have to take this number 4.17, say to myself, is it big enough? Is this a big enough difference between these two boxes for me to reject my null hypothesis? Well, how am I going to figure that out? Well, there's a distribution for chi-square that shows you what's the probability of getting this large a chi-square when the null hypothesis is not true. Right? So let's take a look and see if we can't find that chi-square table. Okay, let's see if I got it. There it is. Oh, no, that's not the right one. Chi-square.doc. I want the table. Chi-square table. There's a table. Okay, I'm going to open up this table. This table is going to give me the critical values of chi-square. Right? So if I look at the probability of seeing the critical value if the null hypothesis is not true, right, is going to be for 10%, alpha is equal to 10%, that this column for alpha is equal to 1%, this column. Most of the time, alpha is going to be equal to 0.05, so we're going to use this column. Well, degrees of freedom, what are the degrees of freedom here? Sample size, or what is it? It's got to do with the number of rows and number of columns. The degrees of freedom are equal to the number of rows minus 1 times the number of columns minus 1. So it's 2 minus 1 is 1, 2 minus 1 is 1, 1 times 1 is 1. This is 1 degree of freedom for a 2 by 2 table. So the value that I have to exceed in order to reject the null hypothesis is 3.841. What is that called again? Critical value of chi-square. Okay, we term that the critical value of chi-square. Working on something else there, that's why that came up. So our critical value, chi-square critical, is equal to 3.8, what was it, 841? 841. And our calculated value of chi-square is 4.17. Can I reject the null hypothesis? Yes, you can. And accept the alternative hypothesis. That makes sense? You guys okay with it? Now, how much nicer a statistic can you want? All you need is a calculator. You can figure it out, and a table, right? It's actually pretty straightforward. Let me see if we have shock and awe over here on the online. Yes.
Is this table standard?
Yes. That's from one of the textbooks. I think that might be from it's not from Aggressively. I think it's from somewhere else. But okay. So how do you guys feel, guys? How are you guys feeling online? Does that make sense to you so far? Okay. I got anybody that's still awake out there? You know, I know there's a lag, so it takes a little while. First of all, it takes about 10 seconds for somebody to screw up their courage to type into that chat box. And then there's the additional lag from the internet. Play it one more time. Oh, degrees of freedom. Degrees of freedom are determined by the number of rows minus 1 times the number of columns minus 1. So for instance, yeah, let me give you another example. Let's say, yeah, let me give you another example. Let's say that we were looking at a situation where, let me move this over and get a little tiny bit of clean space. Let's say that we have people that are a high exposure, a medium exposure, and no exposure, and they got cancer or they didn't get cancer. Cancer plus, cancer minus. How many rows do we have there? How many columns do we have there? We have 3 rows, 3 columns. So that would be 3 minus 1 is 2. 1 minus 1 is 1. So 2 times 1 is 2 degrees of freedom. So the critical value for there would be 5.991. And we would be having to take 6 boxes and do that chi-square calculation there. Okay, I want to do one more thing, and that is I want to show you this calculation using SPSS. Okay, so yeah, definitely I don't think you guys are ready to do this on the test yet. So I want to give you guys a little bit more time. Well, no, this you're going to have to do on the test. The analysis of variance, you know, we're just doing this week, and I don't want to get ahead. I want you to be able to get a closer look at this. And I'll do a review, and I'll try and concentrate a bit on this a little bit more than the other stuff, because we've already done a lot of reviews on the t-test. They're posted, so you can get to them if you want. So let me see if I can't find it very quick. Actually, it's on Blackboard. Now, let me get the Blackboard. And let me get one of these. SAV. Here we go. I'm going to download this. And I'm going to put it on my desktop. I should find that. I've been using this since 2014. I probably should find something new, right? Okay. Okay, what's stenosis? Anybody know what stenosis is?
Yeah.
It's closing of something, right? Like hardening of the arteries. Stenosis is when your spinal column narrows and tightens up on that nerve and stuff, right? So stenosis is either a clogging or a narrowing or something like that. Okay, so we're looking at, I think on this it's arterial stenosis. Let me see if I can't find it quickly. And there it is. I'm going to open it up in SPSS. And we're only gonna be here another 5 minutes. So if you guys are tight for time and you're on your way to a class, just hang in there just for another couple of minutes. Okay. Yeah, I'm really sorry. Somebody typed in they had to leave. I'm sorry about that. I literally spent an hour on the Triborough Bridge on my way over here from Queens. Okay, so let's take a look at this. So this tells us, let's see, we got people who smoke, people who don't smoke, and people who developed stenosis. We also have gender, male and female. 0 and 1 represents male and female. So we could build a 2 by 2. See, we have smoker and not smoker. There's only 2 values. And we have got a disease, has stenosis, doesn't have stenosis. I can go into the variable view. You can see it there. Right? You can see for smokers, the value is yes, they smoked. No, they didn't smoke. For disease, yes, they have stenosis. No, they don't have stenosis. And 0 and 1, female and male. So they're all the dichotomous variables. So I'm going to examine whether or not smoking has an association with stenosis. So my null hypothesis is there's no association between smoking and arterial stenosis, the disease. So I'm going to go up here to analyze, and my alternative hypothesis is that there is an association. And I'm going to test that several ways. I'm going to calculate a chi-square value, compare it to the critical value of chi-square. I'm also going to calculate an odds ratio and a relative risk also. I'm going to go up here to analyze. I'm going to go up to, where is it? Descriptive statistics. You hide it in there, right? Descriptive statistics and crosstabs. It's hidden in there because crosstabs is a way of organizing data to make it a little bit more understandable. So in the rows, I'm going to put the exposure. The exposure is smoking. In the columns, I'm going to put the disease, right? Presence of aortic stenosis. Okay. And now I'm going to go in here. I'm going to go into statistics. And you know, I'm not going to check any of these off right now. First thing I'm going to do is I'm going to go into cells and tell it to show me the observed values. Just make a table. That's all it's going to do right now. So let's go here. And here's our table. We have 215 people. 94 of them are smokers, 121 of them were not smokers. This obviously is maybe an elderly group or something like that. People have a lot of stenosis, or it's just made up data, which it really is, right? So out of the 94 who smokers, 54 of them had signs of stenosis. Out of the non-smokers, 44 out of 121 had stenosis. So how would we calculate our risk? 54 over 94, 44 over 121. And relative risk would be 54 over 94 divided by 44 over 121. How about odds? That would be 54 over 40 divided by 44 over 77 would be our odds ratio, right? That's simple, right? So now, if you wanted to create an expected values, you could go into analyze, you could go into descriptive statistics and crosstabs again, and this time we can go into cells and we can ask SPSS to calculate the expected values as well. And it will do that for us. And it gives us a new table. And the new table has both the observed values and the expected values. It builds it into one table rather than into 2 separate tables. But you can see this is the observed, this is the expected. For non-smokers, this is the observed, this is the expected. Well, now that we have that, I can go back into here to analyze, descriptive statistics, crosstabs, go over here, go back into cells, ask it, calculate the percentages by rows. I'll click OK. Let's see what I get this time. Well, now it gives me a percentage. It gives me 40. There's 54 out of 94 people, and that means that 57% of the smokers developed stenosis. 36% of the non-smokers developed stenosis. In other words, 44 out of 121. So my relative risk would be 57.4 over 36.4. It'd be about, what does that look like? About 1.6 or something like that. 1.5, 1.6 or something like that would be my relative risk. Now, I could actually go here and now calculate chi-square, odds ratio, relative risk using SPSS. I'm going to do that right now. Analyze. I'm going to go into descriptive statistics, crosstabs. Okay, I'm going to turn this stuff off because we don't need it right anymore. I'm just going to stick with observed values. And I'm going to go into statistics and ask it to calculate chi-square for me and to calculate risk. When you click that risk box, obviously chi-square is going to do our chi-square calculation. When you click that risk box, it's going to do odds ratio and relative risk for us as well. I'll click continue and I'll click OK. Okay, so let's take a look at what we have here now. Here is our chi-square value. The version of chi-square that we just did was called Pearson's chi-square. And if you took these numbers and actually took those expected values, observed values, squared them, divided by expected values, each cell, you would literally wind up with the number 9.480. Okay, I'll get into this continuity correction another time, but that is our chi-square value. The probability that you would get that extreme a value if the null hypothesis was true is less than 5%. It's in fact, it's 0.002%. It doesn't give you the critical value, but you know it's 1 degree of freedom. What's the critical value? It's 3.841. So you know it exceeded the critical value. You can look on the table if you want, but you don't really need the critical value because it actually gives you the actual p-value, the actual probability you would be wrong if you reject the null hypothesis, okay, which is less than 5%. So as long as that's less than 5%, you reject the null hypothesis and accept the alternative hypothesis. What about down here? The odds ratio for smoking is 2.363. And wait a second, they gave us a confidence interval for the odds ratio, didn't they? It's 1.361 to 4.1. So since 1 is not in there, you know that the relative risk is not, there's less than 5% chance that that you would be wrong if you reject the null hypothesis, relative risk of once. And here is, we even have remember what we said that the relative risk was? The risk ratio, relative risk was roughly about 1.5, 1.6. Here it is right here. What's the odds ratio for the relative risk? It's 1.179 to 2.18, again, excluding 1. So this, and chi-square are all evidence we can reject the null hypothesis and accept the alternative hypothesis. Okay, guys, unfortunately, I got to get ready for the next class. And I'm sorry about the weather delay. And